scientists are deleting their life's work right now because the James Webb Telescope just photographed something that makes 50 years of physics look like a fairy tale. Thanks to the James Webb Space Telescope, we're seeing something that changes everything we thought we knew about how big the universe really is. You're about to discover why everything you learned about the universe's size might need an update. Are you ready? Let's begin. Before Webb launched on Christmas Day 2021, astronomers relied primarily on the Hubble Space Telescope to study the distant universe. Hubble, operational since 1990, gave us breathtaking images and revolutionary discoveries. It measured the universe's expansion rate, studied the atmospheres of planets around other stars, and captured light from galaxies billions of light-years away. Hubble changed everything we knew about cosmic scale, but Hubble had limitations. It primarily observed visible and ultraviolet light, the same wavelengths your eyes can detect, plus a bit beyond. This works brilliantly for studying nearby objects, but it struggles with the most distant corners of the universe. Here's why. As light travels through expanding space, its wavelength stretches. Light that started as visible or ultraviolet billions of years ago gets stretched into infrared wavelengths by the time it reaches us. Hubble could detect some infrared, but not with the sensitivity needed to see the universe's earliest chapters. Enter James Webb. This telescope is specifically designed to observe infrared light with unprecedented clarity. Its mirror is 6.5 meters across, nearly 3 times Hubble's diameter, giving it dramatically more light-collecting power. Webb sits at a gravitationally stable point called Lagrange 2, about 1.5 million kilometers from Earth, where it maintains a constant position relative to our planet while staying perfectly aligned with the Sun. Webb's instruments are cooled to just a few degrees above absolute zero, necessary because infrared detectors must be incredibly cold to avoid being blinded by their own heat. A massive sun shield the size of a tennis court protects the telescope from solar radiation, keeping one side scorching hot while the other remains frigidly cold. This engineering marvel allows Webb to detect the faintest infrared whispers from the dawn of creation. Within months of beginning operations in mid-2022, Webb started sending back images that stunned the scientific community. The first deep-field image, released in July 2022, showed a patch of sky no bigger than a grain of sand held at arm's length. In that tiny region, Webb captured thousands of galaxies, some of which existed when the universe was only a few 100 million years old. But here's where things get interesting. Those early galaxies look wrong. According to our models of cosmic evolution, the first galaxies should be small, messy, irregular structures, like cosmic toddlers learning to walk. They should be dim and hard to detect. Instead, Webb found massive, mature-looking galaxies in the early universe, some as developed as galaxies we see in the modern cosmos. It's like opening a photo album expecting to see baby pictures and finding images of fully grown adults instead. One galaxy Webb detected, catalogued as JD's GS-Z140, existed roughly 290 million years after the Big Bang. The universe itself is about 13.8 billion years old, which means we're seeing this galaxy as it appeared when the cosmos was only about 2% of its current age. Light from this galaxy traveled for over 13 billion years to reach Webb's mirrors, carrying information from an era when the universe was just beginning to take shape. Another early galaxy, Sears 93316, appears even more puzzling. Spectroscopic analysis suggests it contains stars that are already hundreds of millions of years old, when the universe itself was supposedly only 250 million years old. This creates a timeline problem. Stars need time to form, to live, and to create the heavy elements we detect in their spectra. If we're seeing mature stars this early, when did they actually form? The numbers don't quite add up with our current understanding. These discoveries force us to confront uncomfortable questions about cosmic chronology. Either our models of galaxy formation are incomplete, missing some mechanism that allows galaxies to assemble faster than we thought possible, or our understanding of the universe's age and expansion history needs revision. Both possibilities have profound implications. Let's talk about cosmic scale for a moment, because the numbers involved are so large that they stop making intuitive sense. The observable universe, the part we can theoretically see, extends about 46.5 billion light-years in every direction from Earth. Wait, you might think, didn't I just say the universe is 13.8 billion years old? How can we see objects 46 billion light-years away if light has only had 13.8 billion years to travel? The answer lies in expansion. The universe isn't just sitting still while light travels through it. Space itself is stretching, carrying galaxies along for the ride. A galaxy that emitted light 13 billion years ago wasn't 13 billion light-years away when it released that light. It was much closer. But during the time the light traveled toward us, space expanded, carrying that galaxy further away. Today, that same galaxy is roughly 30 billion light-years distant, even though its light has been traveling for only 13 billion years. This expansion isn't galaxies moving through space like cars on a highway, it's space itself growing, like dots on an inflating balloon getting further apart, even though they're not moving across the balloon's surface. Every point in space is receding from every other point, and the further apart 2 points are, the faster they're separating. This is Hubble's law, discovered by Edwin Hubble in 1929 when he observed that distant galaxies show red-shifted light, their wavelengths stretched toward the red end of the spectrum, indicating they're moving away from us. The expansion rate is described by the Hubble constant, a number that tells us how fast the universe is growing. But here's the problem. We can't agree on what that number actually is. Different measurement methods give different results, and this disagreement has become one of the biggest puzzles in modern cosmology. Webb is making this puzzle even more complicated, but also more interesting. To understand why measuring cosmic expansion is so tricky, we need to talk about the cosmic distance ladder. Imagine you're trying to measure how far away something is. If it's close, you can use parallax, the apparent shift in position when you view it from different angles. Hold your finger in front of your face and close one eye, then the other. See how your finger seems to jump? That's parallax, and astronomers use the same principle with stars. As Earth orbits the Sun, nearby stars appear to shift position slightly against the background of more distant stars. By measuring this shift and knowing Earth's orbital diameter, we can calculate the star's distance through simple trigonometry. This method works beautifully for stars within a few thousand light-years, but beyond that the shifts become too small to measure accurately, even with our best instruments. For more distant objects, astronomers use what are called standard candles, objects with known intrinsic brightness. If you know how bright something actually is and you measure how bright it appears from Earth, you can calculate its distance. It's like seeing a car's headlights at night. You know roughly how bright headlights are, so if they look dim, the car must be far away. One of the best standard candles is a type of exploding star called a type Ia supernova. These occur when a white dwarf star in a binary system siphons matter from its companion until reaching a critical mass, about 1.4 times the Sun's mass. At that precise threshold, the white dwarf explodes with remarkably consistent brightness. No matter where in the universe a type Ia supernova occurs, it releases nearly the same amount of energy, making it visible across billions of light-years. In the late 1990s, two teams of astronomers used type Ia supernovae to measure cosmic expansion at different epochs in the universe's history. They expected to find that expansion was slowing down, decelerated by gravity's pull. Instead, they discovered something shocking. Expansion is accelerating. Distant supernovae appeared dimmer than expected, meaning they were further away than they should be if expansion had been constant or slowing. This discovery earned the 2011 Nobel Prize in Physics and introduced us to one of the universe's deepest mysteries: dark energy. Dark energy is whatever is causing space to expand faster and faster. We don't know what it is. We can't see it or detect it directly. We only know it exists because of its effect on cosmic expansion. The best estimates suggest dark energy makes up about 68% of the universe's total energy content. That means the majority of everything that exists is something we fundamentally don't understand. Think about that for a moment. We've catalogued galaxies, mapped the cosmic web, sent probes to the edge of our solar system, and yet more than 2/3 of reality remains completely mysterious to us. Now here's where Webb enters the story and makes everything more complicated. There are two primary ways to measure the Hubble constant, the universe's expansion rate. The first method uses the cosmic microwave background, the afterglow of the Big Bang. The Planck satellite mapped this ancient light in exquisite detail from 29 through 2013, allowing cosmologists to calculate the early universe's properties and predict how fast it should be expanding today. This method gives a Hubble constant of about 67 kilometers per second per megaparsec. What does that mean? For every megaparsec, about 3.26 million light-years of distance between us and a galaxy, that galaxy is receding at 67 kilometers per second faster. A galaxy 10 megaparsecs away recedes at 670 kilometers per second. One at 100 megaparsecs away recedes at 6,700 kilometers per second. The relationship is linear: double the distance, double the recession speed. The second method uses the cosmic distance ladder we talked about earlier, building up from nearby stars to distant galaxies using standard candles, like Cepheid variable stars and type Ia supernovae. This approach, pioneered by teams using Hubble and now refined with Webb, gives a Hubble constant of about 73 kilometers per second per megaparsec. 6 kilometers per second per megaparsec might not sound like much, but it represents a fundamental disagreement about the universe's expansion rate. This is called the Hubble tension, and it's been growing more pronounced as measurements become more precise. At first, scientists hoped the discrepancy would resolve as techniques improved and uncertainties decreased. Instead, both methods have become more confident in their conflicting results. Webb has made the tension worse, or more interesting, depending on your perspective. By observing Cepheid variables in distant galaxies with unprecedented clarity, Webb has confirmed Hubble's local universe measurements. The higher expansion rate isn't a measurement error. It's real. But the cosmic microwave background measurements are also robust and well-tested. Something doesn't add up. Several possibilities could explain this tension. Maybe our model of cosmic evolution is incomplete. Perhaps dark energy's strength has changed over time rather than remaining constant. Maybe there's new physics we haven't discovered yet, additional particles or forces that affect expansion. Or possibly the universe's expansion isn't uniform in all directions, though this would contradict the cosmological principle that says the universe should look roughly the same everywhere. This is where science gets exciting. We're not just filling in details anymore. We're confronting evidence that our fundamental understanding might be wrong. And that's exactly how breakthroughs happen, when observations refuse to fit into our neat, theoretical boxes. Speaking of scale, if you've ever wondered just how far humanity could actually travel through the vastness we're discussing, I've got a video that explores that exact question. It's called "Scientists Revealed How Far Humans Can Travel Through Space," and it dives into the real physical limits of space exploration, from relativistic speeds to the edge of the observable universe. You'll want to check that out after this. It connects perfectly to what we're talking about here. The link is in the description and on the card above, but let's get back to what Webb is showing us about cosmic scale. Beyond measuring expansion, Webb is revealing structure formation in the early universe. Galaxies don't exist in isolation. They cluster together, forming groups, clusters, and superclusters connected by filaments of dark matter and gas. This cosmic web took billions of years to develop, or so we thought. Webb has detected protoclusters, the ancestors of galaxy clusters, existing when the universe was less than 1 billion years old. These structures contain dozens of galaxies already in the process of merging and interacting. According to simulations of structure formation, it should take several billion years for such dense groupings to assemble through gravitational attraction. Yet here they are, fully formed when the universe is barely out of its infancy. One particularly striking discovery is a protocluster designated SPT2349, observed as it appeared about 12 billion years ago. This massive structure contains at least 14 galaxies in a region only about 170,000 light-years across, smaller than our Milky Way galaxy, yet containing more than a dozen separate galaxies that will eventually merge into a giant elliptical galaxy. The star formation rate in this protocluster is extraordinary, producing stars at a combined rate thousands of times faster than the Milky Way does today. These observations tell us that the universe wasted no time getting organized after the Big Bang. The conventional picture showed a gradual build-up, first stars, then small galaxies, then larger galaxies forming through mergers, and finally clusters assembling over cosmic time. Webb suggests this process happened much faster than our models predicted. To appreciate what Webb is revealing, we need to understand cosmic dawn, the period when the universe's first stars ignited and galaxies began to take shape. This epoch, occurring between roughly 100 million and 1 billion years after the Big Bang, represents one of the most dramatic transformations in cosmic history. Before this, the universe was dark. After it, light flooded the cosmos, fundamentally changing everything. Immediately after the Big Bang, the universe was a hot, dense soup of particles and radiation. Protons, electrons, and photons bounced off each other constantly, creating an opaque fog. Light couldn't travel freely because free electrons scattered photons in every direction, like trying to see through thick mist. This period lasted about 380,000 years, a cosmic eye blink, but an eternity when everything is happening at such extreme temperatures and densities. Then came recombination. As the universe expanded and cooled, electrons combined with protons to form neutral hydrogen atoms. Suddenly, photons could travel freely through space without constantly colliding with charged particles. The universe became transparent. The light released at that moment is what we observe today as the cosmic microwave background, a baby picture of the universe at 380,000 years old, now stretched by expansion into microwave wavelengths. But after recombination came the Dark Ages, a period lasting tens to hundreds of millions of years when the universe contained no light sources. Neutral hydrogen filled space, but no stars had formed yet to illuminate it. The universe was genuinely dark, cooling and expanding in silence, waiting for gravity to pull matter together densely enough to ignite the first fusion reactions. Those first stars were nothing like the Sun. They formed from primordial gas containing only hydrogen, helium, and trace amounts of lithium, the only elements created in the Big Bang. Without heavier elements to help clouds cool and collapse, these first stars had to be enormous, perhaps 100 to 300 times the Sun's mass. They burned incredibly hot and bright, living fast and dying young in spectacular supernova explosions after only a few million years. These massive stars, called population 3 stars, have never been directly observed. They existed too long ago and died too quickly, but their influence shaped everything that came after. When they exploded, they scattered the first heavy elements, carbon, oxygen, iron, and others, into space. These elements, forged in stellar cores and supernova explosions, became the building blocks for the next generation of stars, planets, and eventually life itself. You are made of atoms created in the hearts of ancient stars, scattered across the cosmos, and eventually gathered into the planet where you were born. The light from population 3 stars did something else crucial. It began reionizing the universe. These early stars were so hot that they emitted intense ultraviolet radiation, energetic enough to strip electrons from neutral hydrogen atoms. Around each massive star, a bubble of ionized gas expanded, carving out clear regions in the cosmic fog. As more stars formed and more bubbles expanded, they eventually overlapped, transforming the universe from mostly neutral to mostly ionized over the course of several 100 million years. This epoch of reionization marks the transition from cosmic darkness to cosmic light. Understanding exactly how and when it happened is one of astronomy's major goals, and Webb is specifically designed to study this era. By observing the most distant galaxies, Webb sees them as they appeared during reionization, allowing us to witness this transformation firsthand. What Webb has found challenges our timeline. Galaxies detected from the first 500 million years after the Big Bang are more luminous than expected. They're producing more ionizing radiation, forming stars more rapidly, and organizing into structures more quickly than our models predicted. Some of these early galaxies show evidence of supermassive black holes at their centers, objects containing millions or even billions of solar masses, existing when the universe was supposedly too young for such monsters to have grown. Consider galaxy Sears 1019, observed as it appeared roughly 570 million years after the Big Bang. Spectroscopic analysis reveals it contains a black hole with a mass roughly equivalent to 10 million suns. How did this black hole grow so massive so quickly? Black holes grow by accreting matter, pulling in gas, dust, and even stars from their surroundings. But this process takes time. Even under ideal conditions, there are physical limits to how fast a black hole can grow, determined by radiation pressure pushing against infalling matter. Starting from a stellar mass black hole, perhaps 30 to 100 solar masses, formed from a population 3 stars collapse, and growing continuously at the maximum theoretical rate, called the Eddington limit, a black hole would need at least several 100 million years to reach 10 million solar masses. But if the universe itself is only 570 million years old when we observe this galaxy, and stars needed time to form before collapsing into black holes, the timeline becomes impossibly tight. This suggests either black holes can grow faster than we thought, perhaps through different accretion mechanisms or by merging with other black holes more efficiently, or some black holes didn't form from stars at all. Maybe they were born massive, created directly from the collapse of enormous gas clouds in the early universe. These direct collapse black holes could start with thousands or even tens of thousands of solar masses, giving them a head start on becoming the supermassive black holes we observe. Webb's spectroscopic capabilities are crucial for understanding these objects. When you look at distant galaxies through a telescope, you're not just seeing pretty pictures. Light carries information encoded in its spectrum, the rainbow of wavelengths from infrared through visible to ultraviolet. Different elements absorb and emit light at specific wavelengths, creating a unique fingerprint. By splitting light into its component wavelengths, astronomers can identify which elements are present, how hot the gas is, how fast it's moving, and whether it's being ionized by starlight or something else. Webb's near-infrared spectrograph, called NIR-SPEC, can observe 100 objects simultaneously, measuring their spectra with exquisite detail. This allows astronomers to confirm distances, measuring how much the spectrum has been redshifted by cosmic expansion, and determine physical conditions in these early galaxies. What they're finding is diversity. Some early galaxies are forming stars violently, creating thousands of solar masses worth of new stars every year. Others are more sedate, resembling smaller versions of modern spiral galaxies. This diversity itself is surprising. Theory suggested early galaxies should be fairly similar, chaotic, irregular structures, still in the process of assembling. Instead, Webb sees galaxies with organized structure, spiral arms, and central bulges existing when the universe is less than 10% of its current age. It's like expecting to find only simple, single-celled organisms in Earth's ancient rocks and instead discovering complex multicellular life already thriving. Let's zoom out and think about what this means for cosmic scale. The observable universe contains at least 2 trillion galaxies, each with hundreds of billions of stars spread across a sphere 93 billion light-years in diameter. That's the region from which light has had time to reach us since the Big Bang. But the observable universe isn't the entire universe, it's just the part we can see. Beyond our cosmic horizon, space continues. We don't know if it goes on forever or eventually curves back on itself. We don't know if it's infinite or finite. Current measurements suggest space is flat, meaning parallel lines never converge or diverge, and the universe could extend infinitely in all directions. If that's true, then beyond our observable sphere, there are infinitely many more galaxies, stars, and planets we'll never see because their light hasn't reached us yet and never will due to accelerating expansion. Think about what that means. Everything you can observe, even with the most powerful telescopes, represents an infinitesimal fraction of reality if the universe is truly infinite. All of human history, every civilization, every war and peace, every discovery and tragedy, every person who has ever lived, all of it happens in one tiny corner of one galaxy in a cosmos that might extend forever in all directions. Yet here's the beautiful paradox. Despite being cosmically insignificant, we're also profoundly important. We're the universe becoming aware of itself. We're atoms arranged in such a way that we can contemplate atoms. We're matter that has evolved to study matter. In the entire cosmic volume we can observe, intelligence capable of building telescopes and asking these questions appears to be rare. That makes your existence, your consciousness, your ability to wonder about these things precious beyond measure. Webb reminds us of both our smallness and our significance. When you look at a Webb deep field image showing thousands of galaxies, each containing billions of stars, you're seeing an almost incomprehensible vastness. Yet you're also seeing the fruit of human curiosity and ingenuity. We built instruments capable of detecting light that traveled for over 13 billion years. We developed mathematics to describe cosmic expansion. We created technologies to cool detectors to near absolute zero in the vacuum of space. The telescope itself represents cooperation among thousands of people across multiple continents over several decades. Engineers, scientists, technicians, administrators, all working toward a shared goal of understanding our cosmic origins. Webb isn't just a scientific instrument. It's a monument to what humans can achieve when we direct our intelligence toward questions bigger than ourselves. Now let's talk about what we can't see, the invisible architecture that actually dominates the universe. When you look at Webb's images, you're seeing galaxies, stars, and glowing gas. But those luminous objects represent only about 5% of the universe's total mass and energy. The remaining 95% is dark, invisible to telescopes, detectable only through its gravitational effects. This dark universe is where things get truly strange. Dark matter makes up roughly 27% of the universe's mass-energy content. We know it exists because galaxies rotate too fast. In the 1970s, astronomer Vera Rubin studied spiral galaxies, measuring how quickly stars orbit around the galactic center at different distances. According to Newton's laws, stars farther from the center should orbit more slowly, just like planets farther from the Sun take longer to complete their orbits. Mercury zips around in 88 days, while Neptune takes 165 years. But that's not what Rubin observed. Stars at the edges of galaxies were orbiting just as fast as stars closer to the center, sometimes even faster. This should be impossible unless there's far more mass in galaxies than we can see, mass that doesn't emit light but does exert gravitational pull. She proposed that galaxies are embedded in enormous halos of dark matter, extending far beyond the visible disk, providing the extra gravity needed to explain the rotation speeds. Since Rubin's pioneering work, evidence for dark matter has accumulated from multiple independent sources. Gravitational lensing, the bending of light around massive objects, reveals dark matter's distribution in galaxy clusters. The cosmic microwave background's temperature fluctuations depend on dark matter's influence in the early universe. Computer simulations show that structure formation requires dark matter to explain how galaxies and clusters assembled. Every line of evidence points to the same conclusion. Most matter in the universe is something we've never detected in laboratories. What is dark matter? We don't know. It doesn't absorb, emit, or reflect light. It doesn't interact through the electromagnetic force, which is why it's invisible. It only interacts through gravity, making its presence known by pulling on ordinary matter and bending space-time. Physicists have proposed numerous candidates, exotic particles with names like WIMPs, weakly interacting massive particles, axions, sterile neutrinos, and primordial black holes. Despite decades of experiments, we haven't conclusively detected any of them. Webb can't observe dark matter directly, but it can map its distribution by studying how it affects light from background galaxies. When light from a distant galaxy passes near a massive cluster, the cluster's gravity, dominated by dark matter, bends the light's path, distorting the galaxy's image into arcs or multiple images. By analyzing these distortions, astronomers create maps showing where dark matter concentrates. One stunning example is Webb's observation of the galaxy cluster SMACS 0732, the first deep-field image released in July 2022. This cluster exists about 4 billion light-years away, and its immense mass, mostly dark matter, acts like a cosmic magnifying glass, bending and amplifying light from galaxies behind it, some of which existed over 13 billion years ago. The cluster's gravity creates Einstein rings and elongated arcs, each one a distorted image of a more distant galaxy. By modeling these distortions, astronomers determine the cluster's total mass, finding that dark matter outweighs ordinary matter by roughly 5-to-1. Dark matter provides the gravitational scaffolding upon which galaxies form. In the early universe, dark matter began clumping together first because it doesn't interact with radiation the way ordinary matter does. These dark matter concentrations created gravitational wells, regions where their gravity pulled ordinary hydrogen and helium gas inward. The gas fell into these wells, heated up, and eventually collapsed densely enough to form stars. Galaxies formed where dark matter was already concentrated. Without dark matter, galaxies as we know them couldn't exist, but dark matter is only part of the invisible universe. Dark energy is even more mysterious and more dominant, making up 68% of everything. While dark matter pulls things together through gravity, dark energy pushes things apart, driving cosmic expansion to accelerate. This seems backwards. Gravity should slow expansion, like throwing a ball upward and watching it decelerate. Instead, the universe is speeding up, as if someone keeps adding fuel to the cosmic engine. The discovery of accelerating expansion in 1998 shocked the physics community. Saul Perlmutter, Brian Schmidt, and Adam Rees led the teams that made this discovery using Type Ia supernovae. Their work revealed that expansion was slower in the past and has been accelerating for roughly the last 5 billion years. Something with negative pressure, a repulsive gravitational effect, must be permeating space, counteracting matter's attractive gravity and pushing cosmic expansion faster. Albert Einstein actually predicted something like this decades before its discovery, then called it his biggest blunder. When Einstein developed general relativity in 1915, he realized his equations predicted an unstable universe, either expanding or contracting, but not static. At that time, everyone assumed the universe was eternal and unchanging, so Einstein added a term called the cosmological constant to his equations, providing just enough repulsion to balance gravity's attraction and keep the universe static. Then, in 1929, Edwin Hubble discovered the universe is expanding. Einstein reportedly visited Hubble at Mount Wilson Observatory and, seeing the evidence firsthand, realized his static universe assumption was wrong. The cosmological constant wasn't needed, and Einstein later regretted adding it. But here's the twist. Modern observations suggest the cosmological constant, or something very much like it, actually does exist. Dark energy behaves exactly like the term Einstein introduced and then discarded. What he called his biggest blunder might have been his most prescient insight. What is dark energy? The honest answer is we have no idea. The simplest explanation is that it's an intrinsic property of space itself, a vacuum energy. Quantum field theory predicts that even empty space contains energy due to quantum fluctuations, with virtual particles constantly popping in and out of existence. This vacuum energy would behave exactly like dark energy, providing constant negative pressure as space expands. But there's a colossal problem. When physicists calculate how much vacuum energy quantum mechanics predicts, they get an answer that's 10 to the power of 120 times larger than the dark energy we observe. This is the worst prediction in the history of physics, off by 120 orders of magnitude. It's like estimating someone's height as 1 meter and being wrong by a factor equal to the number of atoms in a trillion universes. Something is deeply wrong with either our understanding of quantum mechanics, our understanding of gravity, or both. Alternative explanations exist. Maybe dark energy isn't constant but changes over time, a possibility called quintessence, after the classical fifth element. Maybe gravity itself behaves differently on cosmic scales than general relativity predicts. Maybe we're observing effects from extraspatial dimensions beyond the 3 we experience. None of these ideas have gained widespread acceptance because they require new physics beyond our current theories, and scientists prefer modifying existing theories only when absolutely necessary. Webb is helping constrain dark energy's properties by precisely measuring cosmic distances and expansion rates at different epochs. By observing Type Ia supernovae in distant galaxies with unprecedented clarity, Webb can determine exactly when acceleration began and whether dark energy's strength has changed over cosmic history. So far, observations are consistent with a cosmological constant, dark energy that remains perfectly constant everywhere and always. But if future observations detect any variation, it would revolutionize physics. Let's consider what dark energy means for the universe's ultimate fate. For most of cosmic history, astronomers debated whether the universe would expand forever or eventually collapse in a big crunch. If there was enough matter, gravity would eventually halt expansion and pull everything back together, ending in a reverse of the Big Bang. If there wasn't enough matter, expansion would continue forever, with galaxies drifting apart until the universe became dark and cold. Dark energy changes this picture entirely. With accelerating expansion, not only will the universe expand forever, but expansion will grow faster and faster with no limit. Galaxies not gravitationally bound to our local group will recede beyond our cosmic horizon, their light redshifted into undetectability. In roughly 150 billion years, observers in the Milky Way, assuming anyone is still around, will see only our local group of gravitationally bound galaxies. Everything else will have disappeared beyond the horizon, making the universe appear much smaller than it does today. Eventually, in trillions of years, even atoms might be torn apart if dark energy continues to dominate. This scenario, called the Big Rip, would occur if dark energy grows stronger over time. First, galaxy clusters would be ripped apart, then galaxies, then solar systems, then planets, then molecules, then atoms. Finally, even atomic nuclei and subatomic particles would be torn asunder as space expands so violently that no force can hold matter together. The universe would end not in fire or ice, but in dissolution, everything scattered into its fundamental constituents, eternally isolated. This is speculative, depending on whether dark energy remains constant or changes. But it illustrates how Webb's observations about cosmic expansion aren't just academic curiosities. They're telling us about the universe's ultimate destiny, about whether reality has a final chapter or continues expanding into eternity. When you think about the universe's structure, you might imagine galaxies scattered randomly through space like stars in the night sky, but zoom out far enough and a breathtaking pattern emerges. Galaxies aren't distributed randomly. They're organized into an intricate cosmic web, vast filaments and sheets surrounding enormous voids, creating a structure that looks eerily similar to the neural networks in your brain or the web of a spider stretching across cosmic scales. This large-scale structure represents the biggest patterns in nature. Individual galaxies cluster into groups containing dozens of members. Groups merge into clusters containing hundreds or thousands of galaxies. Clusters connect through filaments, long strings of galaxies and gas spanning hundreds of millions of light-years. Between these filaments lie voids, immense regions containing very few galaxies, sometimes stretching 500 million light-years across. If you could somehow step outside the universe and look at the distribution of matter, you'd see this foam-like structure extending in every direction. The cosmic web emerged from tiny density fluctuations in the early universe. Immediately after the Big Bang, quantum fluctuations, random variations at the smallest scales, were stretched to cosmic size by inflation, the brief period of exponential expansion thought to have occurred in the universe's first fraction of a second. These fluctuations created regions slightly denser or less dense than average, differences of only 1 part in 100,000. Over time, gravity amplified these tiny differences. Regions slightly denser than average attracted more matter, becoming denser still. Regions slightly less dense lost matter to their denser neighbors, becoming voids. Dark matter, which interacts only through gravity and isn't slowed by pressure or radiation, clumped together first. Its gravity pulled ordinary matter along, creating the filamentary structure we observe today. Computer simulations of structure formation, like the Illustrious project or the Millennium simulation, model billions of particles interacting through gravity over cosmic time. Starting with density fluctuations matching those observed in the cosmic microwave background, these simulations evolve forward through 13.8 billion years of cosmic history. The results are stunning. They produce cosmic web structures nearly identical to what we observe through telescopes. This agreement between simulation and observation strongly validates our understanding of how gravity shapes large-scale structure. Webb contributes to this understanding by observing galaxies at different cosmic epochs, revealing how structure evolved over time. In the very early universe, matter was distributed relatively smoothly. Small density fluctuations existed, but the dramatic contrast between dense filaments and empty voids hadn't yet developed. As time progressed, gravity pulled matter together more tightly, creating increasingly pronounced structure. By observing galaxies at various distances and therefore various times in cosmic history, Webb allows astronomers to create a time-lapse movie of structure formation. Galaxies observed 13 billion light-years away appear as they existed 13 billion years ago, when structure was just beginning to emerge. Galaxies 10 billion light-years away show more developed clustering. Nearby galaxies reveal the mature cosmic web in full glory. Connecting these snapshots reveals how the universe evolved from relative smoothness to magnificent complexity. One of the most interesting aspects of cosmic structure is how galaxies move through it. You might think galaxies simply move away from each other due to expansion, but the reality is more nuanced. Galaxies do recede on average, carried by expanding space, but they also have peculiar velocities, motions relative to the average expansion caused by gravitational attraction toward dense regions and away from voids. These peculiar velocities create cosmic flows. Galaxies drift along filaments toward the densest regions where filaments intersect. Our own Milky Way, for example, is falling toward the Virgo cluster at roughly 400 kilometers per second, pulled by its enormous gravitational influence. But we're also being pulled toward an even more massive structure called the Great Attractor, located about 250 million light-years away in the direction of the Hydra and Centaurus constellations. The Great Attractor itself is falling toward an even larger structure, the Shapley supercluster, the most massive concentration of galaxies in our cosmic neighborhood, containing thousands of galaxies with a combined mass equivalent to tens of thousands of Milky Way galaxies. This creates a hierarchy of motion. Individual galaxies orbit within groups, groups fall toward clusters, clusters flow along filaments toward superclusters, all while the underlying expansion of space carries everything apart on the largest scales. This interplay between expansion and gravitational attraction creates a critical scale in the universe. Structures below a certain size are gravitationally bound. Their internal gravity overcomes expansion, allowing them to remain intact. Our solar system isn't expanding, Earth isn't getting farther from the Sun, the Milky Way isn't growing larger. Even our local group of galaxies, bound by mutual gravity, will remain together indefinitely despite cosmic expansion happening all around us. But beyond gravitationally bound systems, expansion dominates. Distant galaxy clusters are receding from us and will continue receding faster as dark energy accelerates expansion. This creates a cosmic horizon, a boundary beyond which galaxies recede faster than light. Wait, didn't we say nothing can move faster than light? That's true for motion through space, but space itself can expand faster than light, carrying galaxies along for the ride. This doesn't violate relativity because the galaxies aren't moving through space at superluminal speeds. Space between us and them is simply growing. This cosmic horizon currently lies at a distance of about 46.5 billion light-years, defining the edge of the observable universe. Light from objects beyond this horizon has been stretched so much by expansion that it will never reach us. As expansion accelerates, this horizon will eventually encompass fewer galaxies. Objects currently visible will disappear beyond the horizon as space stretches faster than light can traverse it. In the far future, the observable universe will shrink, not because space stops expanding, but because expansion outpaces light's ability to cross cosmic distances. Webb's observations of the cosmic web reveal another fascinating aspect: the intergalactic medium, the gas-filling space between galaxies. For decades, astronomers knew that ordinary matter in galaxies, stars, planets, gas clouds, accounted for only about 10% of the total ordinary matter that should exist based on primordial element abundances from the Big Bang. The remaining 90% was missing, hiding somewhere in the cosmic web. This missing baryon problem was solved when astronomers discovered that most ordinary matter exists in the warm, hot intergalactic medium, tenuous gas with temperatures between 100,000 and 10 million degrees, filling the filaments of the cosmic web. This gas is too hot to emit visible light, but glows faintly in ultraviolet and X-ray wavelengths. It's also so diffuse, less than 1 atom per cubic meter in many regions, that detecting it requires observing its absorption signatures against background light sources. Webb, combined with X-ray telescopes like Chandra and ultraviolet observations from other observatories, is mapping this intergalactic medium, revealing how matter flows along filaments, accretes onto galaxies, and gets heated by shocks and supernovae. This gas represents the raw material for future star formation. As it flows into galaxies, it cools and condenses, eventually forming molecular clouds where stars are born. Understanding this cycle, gas flowing from the cosmic web into galaxies, forming stars, then being ejected back into space by supernova explosions, enriched with heavy elements, is crucial for understanding how galaxies evolve. Some of Webb's most spectacular images show this process in action. The Carina Nebula, imaged in stunning detail by Webb, reveals towering pillars of gas and dust where stars are currently forming. You can see protostars, stars in the process of being born, embedded in cocoons of gas, their infrared radiation illuminating the surrounding material. These stellar nurseries demonstrate that star formation continues throughout cosmic time, not just in the early universe, but even today, 13.8 billion years after the Big Bang. The images also reveal destructive forces. Massive stars, once formed, emit intense ultraviolet radiation that erodes the surrounding gas, carving out cavities and sculpting the nebula into fantastic shapes. When these massive stars exhaust their fuel and explode as supernovae, they blast material into space at tremendous velocities, creating expanding shells of hot gas that sweep up and compress surrounding material, sometimes triggering new generations of star formation. This cycle of creation and destruction occurs throughout the cosmic web. Stars form in dense regions, live for millions or billions of years depending on their mass, then return their material to space through stellar winds or supernova explosions. The heavy elements forged in their cores, carbon, nitrogen, oxygen, silicon, iron, and dozens of others, mix into the intergalactic medium, enriching subsequent generations of stars with heavier element content. Your body contains atoms forged in stars that died billions of years ago before the sun even existed. The calcium in your bones, the iron in your blood, the oxygen you're breathing, all were created through nuclear fusion in stellar cores or explosive nucleosynthesis in supernovae. Those atoms were scattered into space, eventually incorporated into the gas cloud that collapsed to form our solar system 4.6 billion years ago, and ultimately assembled into the complex chemistry of life. This connection between cosmic structure and personal existence is profound. You're not separate from the universe, observing it from outside. You're part of it, made from it, a temporary arrangement of cosmic matter that has gained the ability to contemplate its own origins. The atoms in your hand came from distant corners of the galaxy. The light entering your eyes traveled from the sun, but the energy powering that light came from nuclear fusion, converting hydrogen into helium, releasing energy according to Einstein's equation E equals mc squared. Webb's observations remind us that we're participants in the cosmic story, not just observers. Every breath connects you to stellar nucleosynthesis. Every thought processes information using patterns of electrical activity in neurons made of stardust. Every moment of consciousness represents the universe observing itself, asking questions, seeking understanding. Let's turn our attention from the cosmic web to something closer to home, the search for other worlds. For thousands of years, humans wondered whether planets orbit other stars. Are we alone, or does the universe teem with worlds like Earth? The question seemed unanswerable until 1995, when astronomers Michel Mayor and Didier Queloz detected the first confirmed exoplanet orbiting a Sun-like star. The planet, called 51 Pegasi b, was nothing like anyone expected, a gas giant larger than Jupiter orbiting its star in just 4 days, closer than Mercury orbits our Sun. Since that discovery, we've confirmed over 5,000 exoplanets with thousands more candidates awaiting verification. We've found planets orbiting binary stars, planets around pulsars, worlds larger than Jupiter and smaller than Mercury, scorching hot planets where rock vaporizes and ice-cold planets where nitrogen freezes solid. The diversity is staggering, revealing that planetary systems come in configurations far stranger than our orderly solar system, with rocky planets close to the Sun and gas giants farther out. The Kepler Space Telescope, operational from 2009 through 2018, revolutionized exoplanet discovery by staring at a single patch of sky containing 150,000 stars, watching for tiny dips in brightness when planets pass in front of their host stars. This transit method allowed Kepler to detect thousands of planets, revealing that planetary systems are common. Most stars have planets and potentially habitable worlds, number in the billions in our galaxy alone. But Kepler had limitations. It primarily detected planets around distant stars, hundreds or thousands of light-years away, too far for detailed study. It measured planet sizes and orbital periods but couldn't analyze their atmospheres or compositions. That's where Webb enters the picture, offering capabilities that transform exoplanet science from simple detection to detailed characterization. Webb can analyze exoplanet atmospheres through transmission spectroscopy. When a planet transits its star, some starlight passes through the planet's atmosphere before reaching us. Different molecules in that atmosphere absorb specific wavelengths, creating absorption features in the spectrum. By comparing the star's spectrum when the planet is transiting versus when it's not, astronomers can identify which molecules are present in the planet's atmosphere. In July 2022, Webb delivered its first exoplanet spectrum, observing WASP 96 BB, a hot Jupiter located about 1,000 light-years away. The spectrum showed clear signatures of water vapor, confirming Webb's ability to detect molecules in exoplanet atmospheres with unprecedented precision. Subsequent observations have detected water, carbon dioxide, methane, and other molecules in various exoplanet atmospheres, revealing atmospheric chemistry across different planet types. One particularly exciting observation targeted K218b, a planet roughly 8 times Earth's mass orbiting a red dwarf star about 120 light-years away. This planet lies in its star's habitable zone, the region where temperatures allow liquid water to exist on a planet's surface. Webb's observations detected water vapor and carbon dioxide in its atmosphere, along with possible hints of dimethyl sulfide, a molecule that on Earth is produced primarily by living organisms, particularly marine phytoplankton. Let's be clear, this isn't confirmation of life. Dimethyl sulfide can potentially form through non-biological processes, and the detection needs confirmation through additional observations. But it demonstrates that Webb can detect biosignature gases, molecules associated with life, in the atmospheres of potentially habitable planets. This capability opens the door to genuinely searching for life beyond Earth by analyzing atmospheric chemistry. The search for biosignatures requires understanding what gases indicate biological activity. On Earth, oxygen makes up 21% of our atmosphere, almost entirely produced by photosynthetic organisms over billions of years. Without life constantly replenishing it, atmospheric oxygen would react with surface rocks and disappear within millions of years. Detecting substantial oxygen or ozone, a form of oxygen created when ultraviolet light splits oxygen molecules, would be strong evidence for biological activity on an exoplanet. But oxygen alone isn't definitive. It can be produced abiotically through photochemical reactions in atmospheres rich in water vapor and carbon dioxide. The key is finding combinations of gases that are chemically incompatible, gases that would react and disappear unless something continuously produces them. On Earth, the combination of abundant oxygen with methane represents such a disequilibrium. Methane and oxygen react readily, so their coexistence requires constant production. Life produces both through different processes, creating the chemical imbalance we observe. Webb is searching for these disequilibrium signatures in exoplanet atmospheres, focusing on rocky planets in habitable zones around small, cool stars called M-dwarfs or red dwarfs. These stars are ideal targets because they're small and dim, making the relative brightness change when a planet transits more pronounced and easier to detect. They're also the most common type of star in the galaxy. About 70% of all stars are M-dwarfs, so if planets around them prove habitable, the galaxy contains tens of billions of potentially habitable worlds. However, M-dwarfs present challenges for habitability. They emit most of their energy in infrared rather than visible light, requiring planets to orbit very close to receive enough warmth for liquid water. This proximity subjects planets to intense stellar activity, flares and coronal mass ejections that could strip away atmospheres or bathe surfaces in harmful radiation. Many M-dwarfs are tidally locked, meaning they always show the same face to their star, like the Moon does to Earth. This creates extreme temperature differences between the star-facing side and the dark side, potentially making habitability difficult. Yet recent observations suggest some tidally locked planets might redistribute heat through atmospheric circulation, creating more moderate conditions than expected. And M-dwarfs live for trillions of years, far longer than Sun-like stars, giving life an extraordinary amount of time to emerge and evolve if conditions permit. Some of the oldest stars in the galaxy are M-dwarfs that formed when the universe was less than 1 billion years old, still shining today and likely to continue for trillions of years into the future. Webb has observed several rocky exoplanets around M-dwarfs to determine whether they retain atmospheres. TRAPPIST-1, a star located about 40 light-years away, hosts 7 Earth-sized planets, 3 of which orbit in the habitable zone. This remarkable system drew intense interest when discovered in 2017, as it offers multiple potentially habitable worlds around a single star. Webb observations of TRAPPIST-1b and c, the 2 innermost planets, found no evidence of thick atmospheres, suggesting they've been stripped away by stellar radiation over the system's billion-year history. But TRAPPIST-1 has 5 more planets to study, some farther from the star where atmospheric retention might be more favorable. Webb is systematically observing each planet, building a picture of how planetary atmospheres survive around M-dwarfs. These observations will determine whether the billions of planets around red dwarfs represent habitable real estate or barren, airless rocks baked by stellar radiation. Beyond searching for biosignatures, Webb studies how planetary systems form. Planets coalesce from protoplanetary disks, spinning disks of gas and dust surrounding young stars. The process begins when a molecular cloud collapses to form a star. Conservation of angular momentum causes the collapsing material to flatten into a disk, with the star forming at the center and planets eventually condensing from the surrounding material. Webb can observe protoplanetary disks in exquisite detail, revealing gaps where planets are forming, spiral structures created by gravitational interactions, and variations in disk chemistry that influence what types of planets form in different regions. These observations test theories of planetary formation, helping astronomers understand why some systems produce hot Jupiters while others create multiple rocky planets or icy worlds. One stunning example is Webb's observation of the disk around the star HH 212, located about 1,300 light-years away. The images reveal a disk with distinct gaps and rings carved by planets forming within the disk. As a planet grows, its gravity clears material along its orbital path, creating a gap. The cleared material piles up at the gap's edges, forming rings of enhanced density. By studying gap widths and locations, astronomers can infer the masses and positions of the forming planets, even when the planets themselves are too small and faint to see directly. Webb also observes planetary systems in their death throes. When sun-like stars exhaust their fuel, they expand into red giants, engulfing inner planets and possibly reaching out to vaporize worlds that were once comfortably distant. Eventually, the star sheds its outer layers in a planetary nebula, leaving behind a white dwarf, a dense, Earth-sized remnant containing roughly the Sun's mass compressed into a volume smaller than our planet. Some white dwarfs show metal pollution, heavy elements like iron, magnesium and calcium in their atmospheres that should have sunk into the white dwarf's interior within days or years due to intense gravity. The presence of these elements indicates ongoing accretion of rocky material, likely from asteroids or destroyed planets. By analyzing white dwarf atmospheres, astronomers can determine the composition of destroyed worlds, effectively performing geology on planets that no longer exist. The question of life's origins doesn't begin on planets, it begins in the space between stars. For decades, astronomers have discovered complex organic molecules floating in interstellar space, in the atmospheres of planets, and even in comets and meteorites that fall to Earth. These molecules aren't alive, but they're the chemical building blocks that life requires: amino acids, sugars, nucleobases, and countless other carbon-based compounds. Webb is revealing that organic chemistry happens naturally throughout the cosmos, suggesting that the ingredients for life are common rather than rare. Let's start with what organic means in chemistry. It doesn't necessarily mean biological, it simply refers to molecules containing carbon bonded with hydrogen and often other elements like oxygen, nitrogen, or sulfur. Carbon is special because each carbon atom can form 4 chemical bonds, allowing it to create long chains, branching structures, and complex rings. This versatility makes carbon the foundation of life's chemistry, capable of forming millions of different compounds with diverse properties. The universe produced carbon in stellar cores through nuclear fusion. Inside massive stars, helium nuclei collide and fuse, creating carbon through a process called the triple alpha reaction. When these stars reach the end of their lives and explode as supernovae, they scatter freshly made carbon into space, where it becomes available for forming new molecules. This means every carbon atom in your body was forged in a star's nuclear furnace, expelled into space during the star's death, and eventually incorporated into the molecular cloud that birthed our solar system. In interstellar space, carbon combines with other elements to form molecules in surprising places. Dense molecular clouds, regions where gas and dust concentrate enough to block starlight, serve as cosmic chemistry laboratories. Despite temperatures hovering around 10 to 20 degrees above absolute zero, chemistry proceeds on grain surfaces where atoms meet and bond. Ice mantles on dust grains provide substrates where molecules grow from simple to complex through thousands of reactions over millions of years. Radio telescopes have detected over 200 different molecules in interstellar space, ranging from simple 2-atom molecules like carbon monoxide to complex organic compounds containing dozens of atoms. Glycolaldehyde, a simple sugar, has been detected in star-forming regions. Amino acids have been found in meteorites, and while direct detection in interstellar space remains elusive, related molecules called aminonitriles, precursors to amino acids, have been identified. The chemistry leading from simple molecules to life's building blocks appears to happen naturally wherever conditions permit. Webb contributes to this understanding by observing molecular clouds and star-forming regions in infrared wavelengths, where molecular absorption and emission features are prominent. Webb's mid-infrared instrument, called MIRI, detects the spectral signatures of complex organic molecules, revealing their abundance and distribution in regions where planetary systems are forming. If these molecules are present in protoplanetary disks, they become incorporated into planets and asteroids, delivering organic compounds to planetary surfaces where they might contribute to life's emergence. One of Webb's most significant contributions to astrobiology is studying icy bodies in our own solar system, moons, dwarf planets, and comets that preserve pristine material from the solar system's formation 4.6 billion years ago. These objects act like time capsules containing organic molecules that were present when Earth formed. Understanding their composition helps us reconstruct the chemical inventory available when life emerged on our planet. Europa, a moon of Jupiter, is particularly fascinating. Beneath its icy crust lies a global ocean containing more liquid water than all of Earth's oceans combined. Tidal forces from Jupiter's gravity flex Europa's interior, generating heat that keeps the subsurface ocean liquid despite the moon's distance from the sun. If organic molecules are present in that ocean, and if hydrothermal vents on Europa's seafloor provide energy and chemical gradients similar to those on Earth, Europa might harbor microbial life right now, today, in our cosmic backyard. Webb can't see beneath Europa's ice, but it can analyze the moon's surface and tenuous atmosphere for signs of material brought up from below. Observations have detected carbon dioxide concentrated in certain regions, suggesting exchange between the surface and subsurface ocean. If Webb detects organic molecules or other compounds characteristic of biological activity, it would strengthen the case for Europa as a potentially habitable environment and prioritize it for future exploration by missions designed to sample the subsurface ocean. Enceladus, a small moon of Saturn, presents similar possibilities. In 2005, the Cassini spacecraft discovered plumes of water vapor and ice particles erupting from cracks near Enceladus's south pole. Chemical analysis of plume material revealed not just water, but also salts, organic compounds, and molecular hydrogen, a potential energy source for microbial life. These plumes appear to originate from a subsurface ocean in contact with a rocky seafloor, creating conditions potentially suitable for life. Webb has observed Enceladus's plumes, detecting water, and beginning to characterize their chemistry in detail. Future observations will search for more complex organic molecules and assess whether the plume chemistry is consistent with biological processes. If biosignatures are detected, Enceladus becomes one of the most compelling targets for astrobiological exploration, a place where we might find extraterrestrial life without leaving our solar system. Titan, Saturn's largest moon, represents an entirely different type of potentially habitable environment. Titan's surface temperature hovers around -180 degrees Celsius, far too cold for liquid water. But Titan's dense atmosphere, primarily nitrogen with about 5% methane, creates weather patterns, clouds, and rainfall. Except the rain isn't water, it's liquid methane. Titan has rivers, lakes, and seas of liquid methane and ethane, creating a hydrological cycle remarkably similar to Earth's water cycle, but based on completely different chemistry. Could life exist in liquid methane at temperatures where water is frozen solid? We don't know, but it's theoretically possible. Such life would be radically different from Earth life, using different solvents and possibly different biochemistry. Studying Titan helps us understand what forms of biochemistry might be possible and whether life requires Earth-like conditions or can emerge in exotic environments we haven't imagined. Webb's observations of Titan complement data from the Cassini-Huygens mission, which studied Saturn's system from 2004 through 2017. Webb can observe Titan's atmosphere in infrared wavelengths inaccessible from previous missions, detecting organic molecules and mapping their distribution. These observations prepare for the Dragonfly mission, a rotorcraft planned to launch in 2027 and arrive at Titan in the mid-2030s, where it will fly between different locations, sampling Titan's organic-rich surface and searching for chemical signatures relevant to life's origins. These solar system studies connect directly to exoplanet research. If organic chemistry is common in our solar system, appearing on icy moons, asteroids, and comets, it's likely common in other planetary systems as well. The same processes that delivered organic molecules to early Earth, asteroid, and comet impacts probably occur around other stars. This suggests that planets starting with chemical inventories similar to Earth's might be common throughout the galaxy. But having the right chemistry doesn't guarantee life's emergence. We still don't fully understand how non-living chemistry transitions to living systems. This question, the origin of life, remains one of science's greatest unsolved mysteries. We know life on Earth existed at least 3.8 billion years ago based on chemical signatures in ancient rocks. We know Earth formed 4.6 billion years ago and was heavily bombarded by asteroids and comets for several hundred million years afterward. Somewhere between 4.6 billion and 3.8 billion years ago, during a window of perhaps 500 million to 800 million years, chemistry became biology. How did this happen? Several theories exist. Perhaps life began in tidal pools where cycles of wetting and drying concentrated organic molecules, allowing them to polymerize into longer chains. Perhaps it started at hydrothermal vents on the ocean floor, where chemical gradients between hot, mineral-rich vent fluids and cold ocean water provided energy and chemical raw materials. Perhaps clay minerals served as templates that organized and catalyzed chemical reactions, leading to self-replicating molecular systems. The RNA world hypothesis suggests that early life was based on RNA, a molecule that can both store genetic information like DNA and catalyze chemical reactions like proteins. RNA might have been the first self-replicating molecule capable of copying itself and evolving through natural selection before DNA and proteins took over their current roles. Supporting this idea, scientists have demonstrated that RNA can catalyze its own synthesis under certain conditions, suggesting a plausible pathway from non-living chemistry to primitive life. But we're missing crucial steps. How did the first self-replicating molecule arise from simpler precursors? How did cellular compartments, membranes that separate interior from exterior, develop to contain and protect early biochemistry? How did the genetic code, the mapping between nucleotide triplets and amino acids, get established? These questions remain open, driving research in chemistry, biology, and planetary science. Webb contributes by characterizing the chemical environments where life might emerge. By studying protoplanetary disks, young planetary systems, and diverse planetary atmospheres, Webb maps the distribution of organic molecules and the conditions under which complex chemistry develops. This helps researchers understand what environments are most conducive to life's origins and guides the search for habitable worlds. The search for extraterrestrial life operates on multiple fronts simultaneously. Webb and other telescopes search for biosignature gases in exoplanet atmospheres. Missions to Mars search for fossil evidence of ancient microbial life from when Mars had liquid water on its surface billions of years ago. Future missions will explore Europa and Enceladus, searching for life in subsurface oceans. Radio telescopes listen for signals from technological civilizations, continuing the search for extraterrestrial intelligence that began in 1960. Each approach addresses different possibilities. Life might be microbial and widespread, existing wherever liquid water and organic chemistry coexist. Life might be rare, requiring improbable circumstances that seldom align. Technological civilizations might be common, filling the galaxy with radio signals we simply haven't detected yet. Or we might be alone, the only instance of life in a vast, empty cosmos. Personally, based on what Webb and other missions are revealing about organic chemistry's ubiquity and planetary system abundance, the idea that Earth harbors the only life seems increasingly unlikely. The chemistry leading to life appears common, not rare. Habitable environments number in the billions in our galaxy alone. The time available for life to emerge and evolve extends over billions of years. Given these factors, it seems more probable that life exists elsewhere, possibly commonly, than that Earth represents a unique cosmic accident. But probability isn't certainty. Until we detect life elsewhere, whether microbial life on Mars, aquatic life in Europa's ocean, or technological signals from distant civilizations, the question remains open. And that uncertainty makes the search profoundly important. Discovering even simple microbial life on another world would be among humanity's greatest achievements, answering a question humans have asked since we first looked up at the stars and wondered if anyone was looking back. The question of life in the universe isn't just about finding habitable planets. It's also about understanding whether the chemistry of life, the complex organic molecules that form cells, proteins, and genetic material, is rare and special or common and inevitable throughout the cosmos. Webb is revealing something profound. The building blocks of life are everywhere. Space is filled with organic chemistry, and the molecular precursors to biology form naturally in environments far removed from planets or life itself. Organic molecules, by definition, contain carbon bonded to hydrogen, often with oxygen, nitrogen, sulfur, and other elements mixed in. The term organic doesn't mean biological, it simply refers to carbon-based chemistry. Carbon is uniquely suited for complex chemistry because each carbon atom can form 4 strong bonds with other atoms, allowing the construction of long chains, branching structures, and rings that create molecular diversity. This versatility makes carbon the backbone of life as we know it. For decades, astronomers have detected simple organic molecules in space, methane with 1 carbon atom, formaldehyde with 1 carbon, ethanol with 2 carbons. But in recent years, observations have revealed increasingly complex molecules, polycyclic aromatic hydrocarbons containing multiple carbon rings, amino acids that serve as protein building blocks, and even sugars like glycolaldehyde. These molecules form in interstellar space, in planetary atmospheres, and in the envelopes surrounding dying stars. Webb's infrared vision is perfect for detecting these molecules because organic compounds absorb and emit infrared radiation at characteristic wavelengths. By analyzing the infrared spectra of star-forming regions, planetary atmospheres, and stellar outflows, Webb creates an inventory of cosmic chemistry, revealing which molecules exist, where and how they form. One of Webb's most exciting discoveries involves polycyclic aromatic hydrocarbons, often abbreviated as PAHs. These molecules consist of multiple benzene-like rings, hexagons of carbon atoms with hydrogen attached, fused together into larger structures. On Earth, PAHs form through incomplete combustion and are found in soot, grilled food, and cigarette smoke. In space, they're among the most abundant complex organic molecules, accounting for perhaps 10 to 15% of all cosmic carbon. Webb has detected PAHs in protoplanetary disks, suggesting that planets form in environments already rich in complex organic chemistry. These molecules could be incorporated into forming planets, delivering organic material to rocky worlds from the beginning. This has profound implications for the origin of life, If complex organic molecules arrive with planetary formation, rather than needing to be synthesized from simpler precursors on the planet's surface, the chemical head start could make life's emergence more probable. Webb also studies organic chemistry in the atmospheres of planets and moons in our own solar system. Titan, Saturn's largest moon, has a thick nitrogen atmosphere with methane and ethane clouds. Sunlight drives chemical reactions in Titan's upper atmosphere, creating complex organic molecules that rain down onto the surface, forming lakes, rivers, and seas of liquid methane and ethane, the only known stable liquid bodies on any world besides Earth. Titan's surface chemistry is bizarre by Earth standards. At temperatures around -180 degrees Celsius, water ice is as hard as rock, while methane and ethane remain liquid. Organic molecules accumulate on the surface, creating dunes of hydrocarbon particles and possibly subsurface liquid water oceans beneath the ice shell. Some scientists speculate that Titan might harbor exotic life based on liquid methane rather than liquid water, using completely different biochemistry than terrestrial organisms. Webb's infrared observations can penetrate Titan's hazy atmosphere, revealing surface features and atmospheric chemistry in unprecedented detail. While the Cassini spacecraft studied Titan extensively from 2004 through 2017, Webb provides new spectroscopic data about atmospheric composition and seasonal changes as Titan progresses through its Saturn year, which lasts approximately 29 Earth years. Beyond Titan, Webb observes icy moons like Europa orbiting Jupiter and Enceladus orbiting Saturn. These moons have subsurface oceans beneath ice shells, maintained in liquid state by tidal heating from their giant planet hosts. Gravitational interactions create internal friction, generating warmth that prevents the oceans from freezing solid despite being far from the sun. These oceans contain more water than all of Earth's oceans combined, making them prime targets in the search for life. Enceladus is particularly intriguing because it actively vents water into space through cracks in its south polar ice. The Cassini spacecraft flew through these plumes, analyzing their composition and finding water vapor, ice particles, salts, and simple organic molecules including methane, propane, and acetylene. The plumes appear to originate from hydrothermal vents on the ocean floor, similar to deep-sea vents on Earth where chemosynthetic organisms thrive without sunlight, deriving energy from chemical reactions between seawater and hot rock. Webb can analyze these plumes spectroscopically during periods when Enceladus vents material most actively, potentially detecting more complex organic molecules or even biosignature gases if life exists in the subsurface ocean. Such a discovery would revolutionize biology, demonstrating that life can emerge independently in multiple locations within a single planetary system. The presence of organic molecules throughout the solar system and in interstellar space suggests that prebiotic chemistry, the chemistry leading to life's origin, happens naturally and commonly. But there's an enormous gap between complex organic molecules and actual life. Moving from chemistry to biology requires molecules that can replicate themselves, store information, and evolve through natural selection. Understanding how this transition occurs represents one of science's greatest unsolved problems. On Earth, life emerged relatively quickly. The planet formed 4.6 billion years ago. The earliest evidence for life, isotopic signatures in ancient rocks suggesting biological activity, dates to at least 3.8 billion years ago, possibly earlier. This means life appeared within the first billion years of Earth's existence, despite the planet enduring heavy bombardment by asteroids and comets during much of that period. The rapid emergence suggests that given the right conditions, the transition from chemistry to biology might be reasonably probable. What were those conditions? Earth had liquid water, an energy source from sunlight and geothermal heat, and organic molecules delivered by meteorites or synthesized in the atmosphere through lightning and ultraviolet radiation. The early atmosphere probably contained nitrogen, carbon dioxide, water vapor, and possibly methane and ammonia, providing raw materials for organic synthesis. Lightning, volcanic activity, and ultraviolet radiation drove chemical reactions that created amino acids, nucleotide bases, and other biological building blocks. The famous Miller-Urey experiment, conducted in 1953, demonstrated this principle. Stanley Miller and Harold Urey created a sealed system containing water, methane, ammonia, and hydrogen, then subjected it to electrical sparks simulating lightning. After a week, they found that complex organic molecules had formed, including several amino acids. While subsequent work showed that Earth's early atmosphere probably differed from Miller and Urey's mixture, the principle holds. Given simple starting materials and an energy source, complex organic chemistry emerges naturally. Webb contributes to understanding prebiotic chemistry by observing environments throughout the galaxy where similar processes occur. Star-forming regions like the Orion Nebula contain dense molecular clouds where ultraviolet radiation from young stars drives organic synthesis. Webb's observations reveal which molecules form in these environments and how they're distributed, providing clues about the chemical inventory available to planets forming in such regions. Interstellar ices represent another important source of organic material. In the coldest, densest regions of molecular clouds, molecules freeze onto dust-grained surfaces, forming icy mantles containing water, carbon monoxide, carbon dioxide, methane, ammonia, and more complex species. These icy grains eventually get incorporated into comets. When comets later bombard young planets, they deliver organic, rich material to planetary surfaces. Webb has observed these interstellar ices directly by studying infrared absorption features as light from background stars passes through molecular clouds. The spectra reveal ice composition in extraordinary detail, showing not just which molecules are present but how they're structured and bonded. This information helps scientists understand what materials comets contain and therefore what organic inventory gets delivered to planets during their formation and early evolution. Some scientists propose that life's molecular machinery, particularly RNA, which stores genetic information and catalyzes chemical reactions, might have first emerged not on planetary surfaces, but in interstellar space or within asteroids. The panspermia hypothesis suggests life or its precursors formed in one location and then spread through space via comets, asteroids, or even interstellar dust. While this doesn't answer how life originated initially, it suggests that if life emerges anywhere, it might spread to multiple worlds, increasing the probability of finding it. Evidence for panspermia remains circumstantial but intriguing. Meteorites contain amino acids, including some that don't occur in terrestrial biology, proving that these molecules form extraterrestrially. Some meteorites contain nucleotide bases, the information-carrying units of DNA and RNA. Certain bacteria can survive in space for extended periods, protected within rocks or spacecraft. While this doesn't prove life traveled between worlds, it demonstrates that the ingredients and potentially even simple organisms can survive interplanetary journeys. Webb cannot directly test panspermia, but by revealing how common organic chemistry is throughout the galaxy and how readily complex molecules form in diverse environments, it supports the idea that life's chemical building blocks are universal rather than rare. If similar chemistry occurs everywhere, then wherever conditions permit, liquid water, energy sources, organic molecules, and sufficient time, life might emerge independently. This raises a profound question. If the chemistry of life is common and the ingredients are widespread, why haven't we found evidence of life beyond Earth? The Fermi paradox, named after physicist Enrico Fermi, highlights this puzzle. With hundreds of billions of stars in our galaxy, many billions of years old and potentially billions of habitable planets, where is everybody? If life emerges readily and some fraction develops intelligence and technology, we might expect the galaxy to be teeming with civilizations, yet we see no convincing evidence of extraterrestrial intelligence. Various solutions to the Fermi paradox have been proposed. Perhaps life is common, but intelligence is rare. Maybe technological civilizations destroy themselves before becoming spacefaring. Perhaps interstellar travel is impossibly difficult. Or maybe we're among the first. The universe is young and intelligence takes billions of years to emerge, so we happen to exist during the era when civilizations are just beginning to appear. One of the most profound questions Webb helps us answer is whether the ingredients for life are common or rare. Life on Earth relies on complex organic chemistry, molecules built around carbon atoms forming long chains and intricate structures. DNA, proteins, lipids, carbohydrates, all the molecules essential to biology are organic compounds. For life to emerge elsewhere, those basic chemical building blocks must be available. Webb is discovering that the universe is surprisingly good at making organic molecules, even in environments that seem utterly hostile to life. Space isn't empty. Between stars, within star-forming regions, and throughout planetary systems, space contains diffuse clouds of gas and dust. These molecular clouds, often called stellar nurseries, are where stars and planets are born. They're also cosmic chemistry laboratories where simple atoms combine into increasingly complex molecules. Astronomers have detected over 200 different molecules in space, from simple two-atom molecules like carbon monoxide to complex organic compounds containing a dozen or more atoms. Some of these molecules are directly relevant to biology. Amino acids, the building blocks of proteins, have been found in meteorites that fell to Earth, demonstrating they form naturally in space. Sugars, including ribose, a component of RNA, have been detected in the material around young stars. Polycyclic aromatic hydrocarbons, complex carbon-based molecules, are abundant throughout the galaxy, observed in planetary nebulae, star-forming regions, and even in the diffuse interstellar medium. Webb's infrared capabilities make it ideal for studying these molecules. Organic compounds absorb and emit specific infrared wavelengths corresponding to the vibrations of their chemical bonds. By observing these spectral signatures, Webb can identify molecules even when they're too cold and faint to emit visible light. It's like listening for specific musical notes in a complex symphony. Each molecule produces its unique pattern of absorption and emission features. In star-forming regions like the Orion Nebula, Webb has detected complex organic molecules in the disks surrounding young stars, precisely where planets are forming. This means planets don't form from pristine hydrogen and helium. They inherit a rich chemical legacy, incorporating organic compounds created in the interstellar medium. Earth itself formed from material already containing organic molecules, giving life a head start in terms of available raw materials. Comets and asteroids serve as delivery vehicles for these molecules. During Earth's early history, it was bombarded by countless impacts from these objects, which brought water, organic compounds, and possibly even more complex precursors to life. The Stardust mission returned samples from Comet Wild 2 in 2006, finding amino acids and other organic molecules. The Rosetta spacecraft, which orbited Comet 67P Churyumov-Gerasimenko from 2014 through 2016, detected 16 organic compounds, including 4 found on Earth for the first time in a comet. This suggests a scenario where organic chemistry occurs naturally throughout the universe. Wherever you have carbon, hydrogen, oxygen, nitrogen, and energy sources, all abundant in space, complex organic molecules will eventually form. This doesn't mean life is inevitable, but it removes one potential barrier. The chemical ingredients for life aren't rare or special, they're cosmic commonplace, scattered throughout galaxies, waiting for the right conditions to organize into living systems. But chemistry alone doesn't create life. You need the right environment, liquid water, energy sources, stable conditions over long timescales, and probably some additional factors we don't fully understand. Earth possessed all these requirements. Our planet orbits in the habitable zone, where surface temperatures allow liquid water. It has a protective magnetic field that shields against harmful solar radiation. Its atmosphere provides insulation and pressure to keep water liquid across a wide temperature range. Plate tectonics recycles nutrients and regulates atmospheric composition over geological time. How common are such favorable conditions? This question drives much of astrobiology research. If Earth-like conditions are common, life might be abundant throughout the galaxy. If they're rare, we might be alone or nearly so in our cosmic neighborhood. Webb contributes to answering this question by characterizing rocky exoplanets, determining whether they have atmospheres, identifying atmospheric composition, and searching for signs of surface water. One fascinating target is LHS 1140b, a rocky planet about 1.7 times Earth's diameter, orbiting an M-dwarf star 48 light-years away. Webb observations detected sulfur dioxide in its atmosphere, a molecule produced when volcanic gases react in the atmosphere. This is the first detection of volcanic activity on a planet outside our solar system, revealing that rocky exoplanets can have active geology like Earth, which is important for maintaining atmospheric composition and potentially supporting habitability. Volcanic activity releases gases from a planet's interior, replenishing atmospheric components that would otherwise be lost to space or locked into surface rocks. On Earth, volcanoes release carbon dioxide, water vapor, sulfur compounds, and other gases. This outgassing helped create our early atmosphere and continues to influence atmospheric chemistry today. The carbon dioxide cycle, where volcanic emissions are eventually removed by weathering and locked into carbonate rocks, then released again through subduction and volcanism, regulates Earth's long-term climate, preventing runaway greenhouse heating or freezing. Finding volcanic activity on exoplanets suggests similar processes might operate elsewhere, creating environments where atmospheres are maintained over billions of years, providing stability necessary for life to emerge and evolve. It transforms these worlds from static objects into dynamic systems with ongoing geological processes. Webb also observes Titan, Saturn's largest moon, and one of the most intriguing worlds in our solar system. Titan is the only moon with a thick atmosphere, denser than Earth's, composed primarily of nitrogen with substantial methane. Surface temperatures average -179 degrees Celsius, cold enough that water ice behaves like rock, and liquid. Methane plays the role water does on Earth, forming clouds, rain, rivers, lakes, and seas. Despite being frozen and utterly unlike Earth, Titan has complex organic chemistry. Sunlight breaks apart methane molecules in the upper atmosphere, and the fragments recombine into progressively larger organic molecules. These include tholins, complex organic compounds that give Titan's atmosphere its characteristic orange haze, and possibly even amino acids. Some of these molecules settle to the surface, accumulating over millions of years into deposits of organic material. This makes Titan a natural laboratory for studying prebiotic chemistry, the chemical processes that might lead toward life. While Titan's surface is far too cold for life as we know it, some scientists speculate about exotic biochemistry based on liquid methane instead of water. Even if Titan lacks life, studying its organic chemistry helps us understand how complex molecules form and evolve in planetary environments, providing insights relevant to the early Earth and potentially habitable exoplanets. Beneath Titan's surface lies another intriguing possibility. Evidence suggests Titan harbors a subsurface ocean of liquid water mixed with ammonia, located perhaps 50 to 100 kilometers below the icy crust. This ocean, kept liquid by tidal heating and residual heat from Titan's formation, might provide conditions suitable for life despite the frozen surface above. Several other worlds in our solar system, Europa and Enceladus, moons of Jupiter and Saturn respectively, also harbor subsurface oceans, potentially making ice-covered ocean worlds more common habitable environments in the galaxy than Earth-like terrestrial planets. Webb's observations of Titan complement upcoming missions like Dragonfly, a nuclear-powered rotorcraft scheduled to launch in 2027 and arrive at Titan in the mid-2030s. Dragonfly will fly between dozens of locations on Titan's surface, sampling the organic chemistry and searching for chemical signatures that might indicate prebiotic processes. Together, Webb and Dragonfly will provide unprecedented understanding of one of the solar system's most enigmatic and potentially important worlds for astrobiology. Looking beyond individual planets, Webb studies the galactic environment where planetary systems form. Not all regions of the galaxy are equally favorable for life. The galactic habitable zone, a concept analogous to the habitable zone around stars, describes regions where conditions favor planetary habitability. Too close to the galactic center, frequent supernova explosions and intense radiation from the central supermassive black hole might sterilize planets repeatedly. Too far toward the galactic outskirts, heavy element abundance drops, potentially making rocky planet formation less common. Our solar system orbits in what seems to be a favorable location, about 26,000 light-years from the galactic center, in a relatively quiet region between spiral arms where star formation is moderate and supernova rates are lower than in denser regions. This might be necessary for complex life to evolve. Simple microbial life might be resilient enough to survive periodic radiation bursts, but complex multicellular organisms requiring stable conditions over hundreds of millions or billions of years might need the relative calm of mid-galaxy locations. Webb observes star-forming regions throughout the galaxy, revealing how stellar birth rate and planetary formation vary with location. These observations help constrain estimates of potentially habitable planets galaxy-wide. If habitable zone planets are common, heavy elements are sufficiently abundant in most regions, and subsurface oceans provide additional habitable environments, the galaxy might contain billions of worlds where life could potentially exist. But potential habitability doesn't guarantee life exists, much less intelligent technological life capable of communication. The Drake equation, formulated by astronomer Frank Drake in 1961, attempts to estimate the number of communicative civilizations in the galaxy by multiplying factors like star formation rate, fraction of stars with planets, number of habitable planets per system, fraction where life actually arises, fraction where life becomes intelligent, fraction developing technology, and how long technological civilizations survive. The uncertainties are enormous. We have decent estimates for the early factors, star formation rates, planetary abundance, but the biological and sociological factors remain deeply uncertain. Does life emerge inevitably given the right conditions, or does it require improbable accidents? Does intelligence arise readily from complex life, or was it a unique fluke on Earth? Do technological civilizations typically survive for thousands or millions of years, or do they tend to self-destruct shortly after achieving the capability? Webb can't answer these questions directly, but it provides crucial data for some factors. By determining how many rocky planets exist in habitable zones, by characterizing their atmospheres and searching for biosignatures, by revealing how common the chemical ingredients for life are throughout the cosmos, Webb helps constrain the cosmic census of potentially inhabited worlds. Life as we know it requires several key ingredients. Water serves as a universal solvent, allowing molecules to interact and react. Carbon forms the backbone of complex molecules due to its ability to create stable bonds with other carbon atoms and diverse elements like hydrogen, oxygen, nitrogen, and phosphorus. Energy drives chemical reactions uphill, allowing simple molecules to combine into more complex structures. And time permits the countless chemical experiments nature conducts as molecules collide, react, and occasionally form something more organized. For decades, scientists assumed organic molecules, compounds containing carbon, were rare in space, requiring the special conditions of planetary surfaces to form. But observations have revealed that organic chemistry flourishes throughout the cosmos. Simple organic molecules like methane exist in interstellar gas clouds. More complex organics form in the atmospheres of planets and moons, and laboratory experiments show that exposing simple molecules to ultraviolet light or electrical discharges, simulating conditions in space or early planetary atmospheres, readily produces amino acids, the building blocks of proteins. Webb is revealing that organic chemistry is even more widespread and complex than previously recognized. In molecular clouds where stars form, Webb detects signatures of polycyclic aromatic hydrocarbons, complex carbon-based molecules consisting of multiple connected rings of carbon atoms. These molecules, abbreviated as PAHs, are remarkably stable and abundant, existing in regions where intense radiation would destroy simpler compounds. PAHs are significant because they represent a bridge between simple molecules like methane and the more complex chemistry necessary for life. On Earth, PAHs form through incomplete combustion of organic material. They're found in charcoal, soot, and grilled food. In space, they likely form through chemistry in stellar atmospheres or in the cooling gas around dying stars, then spread throughout the galaxy, becoming incorporated into molecular clouds and eventually into planetary systems. Some scientists speculate that PAHs might play a role in prebiotic chemistry, the chemical processes leading to life's emergence. Their stable ring structures could serve as scaffolds for more complex molecules. They absorb ultraviolet light, potentially protecting other molecules from radiation damage. And they've been detected in meteorites that fell to Earth, demonstrating that these complex organics existed in our solar system's birth cloud and were delivered to the young Earth through asteroid and comet impacts. Speaking of meteorites, we should discuss how Earth acquired the ingredients for life. Our planet formed 4.6 billion years ago from the protoplanetary disk surrounding the young Sun. The inner solar system, where Earth formed, was hot, too hot for volatile compounds like water to condense. This creates a puzzle. Earth today is about 70% covered by oceans, and water exists throughout the crust. Where did all that water come from? The leading explanation is that water was delivered to Earth after the planet cooled, primarily through asteroid and comet impacts during a period called the Late Heavy Bombardment, occurring roughly 4 billion years ago. Asteroids from the outer asteroid belt, which formed beyond the snowline where water could exist as ice, were perturbed into Earth-crossing orbits, delivering water and organic compounds through countless impacts over millions of years. Evidence supports this scenario. Measurements of water's isotopic composition, specifically the ratio of deuterium, a heavy form of hydrogen, to normal hydrogen in Earth's oceans, match the ratios found in certain types of asteroids better than those in most comets. This suggests asteroids delivered the majority of Earth's water, with comets contributing a smaller fraction. These impacts didn't just deliver water. They brought organic molecules, ammonia, methane, and other compounds that enriched the young Earth's chemistry. This delivery mechanism might be universal. Planetary systems forming throughout the galaxy experience similar processes, volatile compounds condensing beyond the snowline, then being delivered to inner rocky planets through gravitational perturbations and impacts? If so, the ingredients for life might be delivered routinely to countless worlds wherever planetary systems form. Webb observes this process happening in other stellar systems. By studying protoplanetary disks, Webb can map the distribution of water, organic molecules, and other volatiles, revealing where in the disk different compounds exist and how they might be incorporated into forming planets. And these observations show that water ice is common in the outer regions of protoplanetary disks, exactly where we'd expect based on our solar system structure. One particularly interesting target for Webb is the icy moons of the outer solar system. Jupiter's moon Europa and Saturn's moon Enceladus both possess subsurface oceans beneath thick ice shells. These oceans contain more liquid water than all of Earth's oceans combined and remain liquid due to tidal heating. Gravitational interactions with their parent planets flexing the moon's interiors, generating heat through friction. Europa's ocean lies beneath an ice shell perhaps 10 to 15 kilometers thick and could be 100 kilometers deep. Enceladus has geysers erupting from cracks near its south pole, shooting water vapor and ice particles hundreds of kilometers into space. The Cassini spacecraft flew through these plumes, detecting water, salts, organic molecules, and molecular hydrogen, evidence of hydrothermal activity on the ocean floor, where hot water interacts with rocky material. These subsurface oceans represent potentially habitable environments, shielded from the harsh radiation of space by kilometers of ice. Hydrothermal vents on their ocean floors might provide energy and chemical disequilibrium, similar to vents on Earth's ocean floor that support thriving ecosystems independent of sunlight. On Earth, these vent communities include tube worms, clams, and microorganisms that derive energy from chemical reactions between hot vent fluids and cold seawater, rather than from photosynthesis. If life exists in Europa's or Enceladus's oceans, it would demonstrate that biology can emerge independently of sunlight, requiring only liquid water, chemical energy, and time. This would profoundly expand the potential habitability of the cosmos. Sunlight-dependent biospheres require planets in narrow, habitable zones around stars, but if life can thrive in subsurface oceans heated by tidal forces, then countless moons throughout the galaxy, orbiting giant planets far from their stars, might harbor biospheres we've never imagined. Webb can't observe these subsurface oceans directly, but it can analyze the composition of surface ice and erupted material, searching for organic molecules and other indicators of ocean chemistry. These observations complement planned missions like NASA's Europa Clipper and ESA's JUICE mission, which will study Jupiter's icy moons in detail, measuring ice shell thickness, mapping surface geology, and analyzing plume composition. Beyond our solar system, Webb is revealing that water exists throughout the galaxy. It's been detected in protoplanetary disks, in the atmospheres of exoplanets ranging from hot Jupiters to potentially habitable rocky worlds, and in interstellar clouds. Water is remarkably common because its constituents, hydrogen and oxygen, are the first and third most abundant elements in the universe. Wherever these elements exist in appropriate conditions, water forms readily. This ubiquity suggests that water-based life might be common if it emerges readily from the right chemical ingredients. But we face a profound puzzle. Despite decades of searching, we've found no convincing evidence of life beyond Earth. No radio signals from alien civilizations. No obvious signs of technology or terraforming. No unambiguous biosignatures in exoplanet atmospheres. This apparent absence, despite the universe's vastness and age, is called the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" Various explanations have been proposed. Perhaps life emerges rarely, requiring an improbable sequence of chemical events. Maybe life emerges commonly, but intelligence arises rarely. Earth spent 3.5 billion years hosting only microbial life before complex multicellular organisms appeared. Perhaps intelligent civilizations inevitably destroy themselves through war, environmental collapse, or technological disasters before they can colonize the galaxy. Or maybe advanced civilizations exist but remain quiet, either disinterested in contact or deliberately avoiding revealing their presence. Another possibility is that we're simply looking at the wrong time or in the wrong ways. The universe is 13.8 billion years old, but the galaxy is relatively young. Most stars formed within the last few billion years. Sun-like stars live about 10 billion years, meaning the first generations of such stars are only now reaching old age. Perhaps intelligence requires billions of years of biological evolution, and we're among the first civilizations to emerge. If so, the galaxy might be empty not because life is rare, but because we're pioneers exploring a cosmos that will eventually teem with life but hasn't reached that stage yet. Webb can't answer the Fermi paradox directly, but by revealing how common habitable conditions are, water, organic molecules, stable planets in appropriate orbits, it helps constrain the equation. If the ingredients for life exist nearly everywhere, then life's absence would point toward biological or evolutionary bottlenecks, steps in the path from chemistry to intelligence that are extraordinarily improbable. If, conversely, habitable conditions prove rare, then life's scarcity would be less surprising. What's certain is that Webb is transforming our understanding of habitability from abstract speculation to concrete observation. We're measuring the atmospheric composition of potentially habitable worlds. We're cataloging organic chemistry throughout the galaxy. We're studying how planetary systems form and evolve. Each observation refines our understanding of where and how life might emerge, bringing us closer to answering the ancient question, are we alone? And regardless of whether we find life elsewhere, Webb's observations remind us that we're part of a vast cosmic ecosystem. The carbon in your DNA, the oxygen you breathe, the water in your cells, all came from space, forged in stars or delivered by asteroids. You're not separate from the cosmos, you're an expression of it, a temporary organization of matter that has gained the ability to contemplate its origins and wonder about its place in existence. These studies reveal that planetary systems like ours are common. Rocky material exists around countless stars. Water, essential for life as we know it, appears widespread throughout the galaxy. Organic molecules, the carbon-based compounds that form the basis of biological chemistry, pervade interstellar space. The ingredients for life seem to be universal, distributed throughout the cosmos by the same stellar and chemical processes that created our solar system. Webb has detected complex organic molecules in regions of active star formation, in protoplanetary disks where planets are coalescing, and even in the atmospheres of comets and distant moons. These molecules include polycyclic aromatic hydrocarbons, ring-shaped carbon structures that represent some of the most stable and abundant organic molecules in space. On Earth, these compounds are found in coal, petroleum, and charred food. In space, they form through chemical reactions in the outflows of dying stars and in dense molecular clouds. The presence of organic molecules throughout space suggests that the chemical building blocks of life aren't rare or special products of Earth's unique history. They're natural consequences of carbon chemistry, forming wherever conditions allow carbon atoms to bond with hydrogen, oxygen, nitrogen, and other common elements. This has profound implications for astrobiology. If organic chemistry is universal, then the emergence of life might not require unlikely coincidences. It might be a natural outcome when the right conditions persist for sufficient time. Consider the amino acids, the molecular building blocks of proteins. Amino acids have been found in meteorites that fell to Earth, including the Murchison meteorite that landed in Australia in 1969. Analysis of this meteorite revealed over 90 different amino acids, including some used by terrestrial life and many others never found in living organisms. This demonstrates that amino acid synthesis occurs naturally in space through non-biological processes, delivering these crucial molecules to planetary surfaces via meteorite impacts. The Rosetta spacecraft, which orbited Comet 67 P. Churyumov-Gerasimenko from 2014 through 2016, detected glycine, the simplest amino acid, directly in the comet's coma, the cloud of gas and dust surrounding its nucleus. It also found phosphorus, a key component of DNA and cell membranes. These discoveries strengthen the hypothesis that comets and asteroids delivered organic molecules and water to the early Earth, providing the raw materials from which life emerged. Webb contributes to this story by observing molecular clouds, the vast cold regions where stars and planets form. These clouds contain complex chemistry, with hundreds of different molecules detected through radio and infrared observations. Simple molecules like water, carbon monoxide, and ammonia are abundant. More complex species include formaldehyde, methanol, ethanol, acetone, and even ethylene glycol, antifreeze. The diversity is remarkable, demonstrating that interstellar chemistry produces molecules of increasing complexity through gas phase reactions, surface chemistry on dust grains, and energetic processing by ultraviolet light and cosmic rays. One particularly interesting discovery is the detection of chiral molecules in space. Chirality, or handedness, refers to molecules that exist in two mirror image forms, like your left and right hands. These forms, called enantiomers, have identical chemical formulas, but different three-dimensional arrangements. In most chemical reactions, both forms are produced in equal amounts, creating a racemic mixture. But terrestrial life shows a striking preference for specific enantiomers. All amino acids in proteins are left-handed. All sugars in DNA and RNA are right-handed. This homochirality is essential for life's function. Proteins fold correctly only when built from amino acids of the same handedness. The origin of this preference remains one of biology's great mysteries. Did it arise randomly on Earth, or does it reflect some asymmetry in the fundamental chemistry of life's origins? Observations of polarized light in star-forming regions suggest that certain regions of space might have slight enantiomeric excesses, more of one form than the other, created by circularly polarized ultraviolet light from nearby massive stars. If organic molecules formed in these regions were delivered to early Earth by comets and meteorites, they might have seeded our planet with a slight chiral bias that life then amplified. This remains speculative, but Webb's observations of star-forming regions and protoplanetary disks might eventually reveal whether enantiomeric excesses exist in the regions where planetary systems form. The search for life extends beyond rocky planets in habitable zones. Some of the most promising locations for life in our own solar system are icy moons with subsurface oceans. Europa, orbiting Jupiter, has an ice shell covering a global ocean containing more water than all of Earth's oceans combined. The ocean is kept liquid by tidal heating, gravitational interactions with Jupiter and other moons flexing Europa's interior, generating heat through friction. Similar oceans likely exist beneath the ice of Enceladus and Titan, moons of Saturn, and possibly Ganymede and Callisto, additional moons of Jupiter. The Cassini spacecraft, which orbited Saturn from 2004 through 2017, detected plumes of water vapor erupting from cracks in Enceladus's icy surface. Analysis of these plumes revealed water, organic molecules, and minerals consistent with hydrothermal activity on the ocean floor. Hydrothermal vents on Earth support thriving ecosystems independent of sunlight, deriving energy from chemical reactions between hot water and rock. If similar vents exist on Enceladus, they could provide energy and nutrients for life. Webb cannot directly observe these subsurface oceans, but it can analyze the composition of surface ice and plume material when moons transit Jupiter or Saturn, using the giant planet's reflected light as a background source. Future missions, including NASA's Europa Clipper and ESA's Jupiter Icy Moons Explorer, will study these moons in detail, searching for signs of habitability and possibly life itself. The concept of habitability has expanded dramatically in recent decades. We once thought life required conditions similar to Earth's, a rocky planet with liquid water at moderate temperatures orbiting a sun-like star. Now we recognize that life might thrive in environments we once considered impossibly hostile. Extremophiles on Earth, organisms that survive in extreme conditions, have been found in boiling hot springs, acidic lakes, radioactive waste, deep underground, and in Antarctic ice. If life can adapt to such diverse environments on Earth, perhaps it can exist in equally diverse settings elsewhere. This expanded conception of habitability multiplies the potential locations where life might exist. The habitable zone around a star is no longer a narrow ring where temperatures permit surface liquid water. It now includes icy moons with subsurface oceans, planets with thick atmospheres that create greenhouse warming, and possibly even rogue planets, worlds ejected from their planetary systems, wandering through interstellar space with no star at all, but potentially maintaining subsurface oceans through radioactive decay and tidal heating from large moons. Webb's observations of diverse planetary environments, from scorching hot Jupiters to frigid ice giants to temperate rocky worlds, reveal that the galaxy contains a staggering variety of worlds. Each represents a different set of conditions, a different chemical environment, a different possibility for the emergence or existence of life. Some might harbor life fundamentally similar to Earth's, based on carbon chemistry and liquid water. Others might host life so different from terrestrial biology that we'd struggle to recognize it as alive. This brings us to one of astrobiology's central challenges. How do you recognize life that's fundamentally different from anything you've encountered? We understand terrestrial biochemistry, DNA, RNA, proteins, cells with membranes, metabolism based on specific chemical reactions. But must all life follow this template? Could silicon replace carbon as the backbone of biological molecules? Could ammonia or methane substitute for water as life's solvent? Could life exist without cells as self-replicating chemical cycles in rocks or clouds? These questions aren't just philosophical speculation, they're practical considerations for the search for life beyond Earth. If we look only for Earth-like biosignatures, oxygen, ozone, methane, chlorophyll, we might miss life that operates through different chemistry. Designing experiments to detect truly alien life requires thinking beyond our terrestrial experience, considering the broadest possible definition of what constitutes a living system. Some scientists define life by its functional properties: metabolism, growth, reproduction, response to stimuli, evolution through natural selection. Any system exhibiting these properties might qualify as alive, regardless of its chemical composition. This functional definition guides the search for weird life, hypothetical organisms based on biochemistry fundamentally different from Earth's. While no such organisms have been found, their possibility keeps astrobiologists thinking broadly about where and how to search. Webb's contribution to astrobiology extends beyond direct observations. Its discoveries about the early universe, galaxy formation, and cosmic chemistry inform our understanding of life's cosmic context. When did conditions suitable for life first arise? The earliest stars contained almost no heavy elements, only hydrogen and helium from the Big Bang. Rocky planets require elements like carbon, oxygen, silicon, and iron, elements forged in stellar cores and scattered by supernovae. Only after the first generations of stars lived and died could planets like Earth form. Webb's observations of galaxies existing 500 million years after the Big Bang reveal that element production began early. Massive stars in these ancient galaxies were already creating and dispersing heavy elements, enriching the intergalactic medium with the raw materials for planets and life. Within the first billion years, the universe contained sufficient heavy elements for rocky planets to form. This means potentially habitable worlds could have existed for over 13 billion years, giving life an extraordinarily long time to emerge, evolve, and perhaps develop intelligence. Have you ever imagined how small we are inside the Milky Way? Check out this video at the left side of the screen. Discover how our solar system is just a tiny speck in the Orion Arm, how the Gaia mission and Hubble Space Telescope have mapped our galactic neighborhood, and why dark matter, spiral arms, and the galactic habitable zone shape the conditions for life. See you there.